Legend has it that about 300 years ago, Sir Isaac Newton fell asleep at the foot of a tree. And while he was sleeping there, an apple fell on his head. Because the apple fell, he realized the idea of gravity. And from there, 300 years later, my life sucks as a physics major. Now it's our time to take revenge. We're going to kill him using his own laws. We're going to use two different scenarios. We're going to use one scenario in which he's just chilling there and a huge apple pops down. Like, I'm talking about like GMO level apples. Like year 3000 we grow apples the size of mamas. That was a terrible joke. And then the other scenario is we're basically like the best baseball player in the world, and we've got an apple here and we're chucking it down on his head. We're going to calculate a very heavy mass to find out what is going to be required for this apple to be able to crush his skull off of just simply dropping it. Good catch. So, based on a quick Google search, the force required to crack a skull is roughly 2,300 newtons. It's funny that we're using newtons for this because we're going to crack his skull using it. Hey, who cares? So using his second law, force equals mass times acceleration. You know, everybody knows that or something, whatever. We have that force. Now we're going to need to find what the acceleration is. We're hoping that Isaac Newton was born on the Earth, and he's on the Earth at this point, and he's not some sort of alien sent from planet Globnar to kill us all. All of us physics majors, of course. But I digress. We're going to use the Earth's gravity for this, for the acceleration g, otherwise known as 9.81 meters per second squared. Now, I understand that this should be a negative acceleration because it's going down, but I don't care because, you know, who cares? Anyways, using this equation, force equals mass times acceleration, we're going to replace that. 2,300 newtons equals mass times 9.81 meters per second squared. We're going to divide that over. We're going to have 2,300 newtons over 9.81 meters per second squared equals the mass. We're going to cancel those out. We're going to get something in kilograms, and that is going to be, let me look at my calculation real quick. That's a big number. That's a pretty big number. 200! That's a 3. 234.45? Was it 4.5? 4.5 kilograms. For the record, that's a lot of pounds in American numbers. I don't know what it is. You do the work. I already got this number. So we would need an apple of mass 234.45 kilograms to crush Sir Isaac Newton's skull, or crack it rather. Now, let's say we're wrong because we didn't take into account air resistance. Oh no, we didn't take into account air resistance. His skull isn't cracked. Well, here's the funny thing. You drop anything near this mass on anyone's skull, they're going to die. It doesn't matter. They're going to die. Let's imagine we don't have the benefits of having a supermassive apple. Because admittedly, that's one of the more unrealistic things of this example, other than the time travel part, the intent to murder Newton, and, you know, the ability of us to do that. All sorts of things just don't make sense in this example. But we're scientists today. We are physicists. And as physicists, one of us has a really strong arm. So today, we're going to use a normal apple to kill Newton. Now, we have to define a couple things, and we'll get to that, but first, let's just rewrite the equation. Force, wow, this is, okay, equals mass times acceleration. But uh-oh, this mass is very tiny. How are we going to do this? Well, we can rewrite this equation to also be force equals mass times the change in velocity, final minus initial, over the change in time. Cool? Cool? You guys got that? You guys got that? Write that down in your notes. Now we can simply divide that over. Force over mass equals VF minus VI over TF minus TI. And bammo! We can work with this. We've got something going. But then we've got a little problem. There's 4 things here. Fortunately for us, 2 of those things are 0. We can say that the final velocity of the apple, as it is falling to the ground, since it's going to hit his skull, it's going to be 0. As soon as it contacts with it, bonk, 0. Final velocity equals 0. Let's write that down somewhere. We've also got the initial time. Ti equals 0, because we're starting at 0. It wouldn't make sense to start at 24 seconds. It's like, oh, we're 24 seconds in, drop it. No, we're not doing that. Also, we need to know what the mass of the apple is. I looked it up. The average mass of an apple is about 1 kilogram. No, it's not 1 kilogram. It's 0.1 kilograms. That would be a very heavy apple if it was 1 kilogram. Now, this is probably about 0.1 kilograms. I could measure this with weights, but yeah, that's 0.1 kilograms. Mass equals 0.1 kilograms. Okay, cool. So we've got something going. We're going to use the same thing from previous, is 2,300 newtons over 0.1 kilograms equals V negative V naught over T final. We can just simplify that to be 23,000 meters per second squared equals negative VI over TF. But this brings a very interesting thing, because there's 2 unknowns here. There's the velocity and the amount of time it takes. Now, this is where a couple assumptions are going to come in, because we're going to use a kinematic equation that I'm going to look at right now because I kind of forgot, known as the displacement equals the change in velocity. So, Vf minus V naught over 2 times time, right? Now, we are allowed to define how tall this tree is. And for the point of this video, we're going to make this tree be 5'10", because Sir Isaac Newton was 5'6", and I am 5'7", and my friend here, who is filming this, is 5'10". I'm pretty close to being his height. We have an apple here. Let's just simulate him dropping it on my head, because why not?
Yep.
Here we go.
Ow. We
I
missed
didn't
your
even-
head. We have to do it again.
We have to do it again?
Yes. Right.
Okay,
It has to hit your head.
Okay, run it back. Here we go. Jeez. Yeah, no, that would definitely hurt him. Why did we do that? Anyways, let's get back to the math. Now that we know this is a 5'10" tree, otherwise known as, I don't know. Let's just say the displacement delta x is going to be 0.92 meters. Okay, delta x equals 0.92 meters. Then we have that. Remember, v final is 0. We have that 0.92 equals times 2, which is going to be about 1.84 meters, is going to be equal to V naught T. With this, negative V naught T. That could have been bad. Yeah, I forgot. With the calculations done, we can see that the time it will take will be 0.009 seconds. So very small, very small amount of time. And the velocity will be, this is a negative number, but who cares? Who cares? I'm just gonna write it. 205.7 meters per second. Divide those two, bam, you've got that number. So, what have we learned from this? You're either gonna need a super thrower for this, because The world record for throws, the fastest throw, is 46.9 meters per second. That's over 4 times. This is over 4 times that. So to crack Isaac Newton's skull, we're gonna need a fast throw, or a very heavy apple, or maybe like a decent size, like you know, a very, like it's a heavy apple, but it's not like exceptionally heavy. Like it's not like you know, triple my weight. But like, for you guys, I want you guys to comment down below what next science thing you want me to talk about, because I have some plans, right? The next 2 aren't going to be physics related at all. I'm a physicist, so we'll see how those go. But if you have any science questions, just feel free to ask them. I might cover them, especially if it's physics related. Dude, I can do the heck out of physics, or astronomy. It's also part of my major. If you liked this video, share it with a physics friend. Also, I forgot to say, don't throw apples at people. I don't condone violence. If you're going to throw this apple, hit the subscribe button first. Yeah, that's the only kind of violence I condone, is hitting the subscribe. Why do I keep hitting this? I don't,